Good morning, everyone. My name is Tony Kojundic. You all grabbed my business card there, K-O-J-U-N-D-I-C. Just call me Tony, please. With the Silica Fume Association. Our association actually sponsored here today by the Federal Highway Administration. As you can see in the one booklet that you guys picked up there, the book was, the Silica Fume User Manual was published by both the SFA and the FHWA, Federal Highway Administration. And part of that effort is what they call technology transfer, sharing what's been done in concrete technology over the last 30 years or so, trying to expedite the learning curve of the next generation, you guys coming up through the ranks. Before we get started, I want to play a little tape here to give you a little bit of background here, which you know which button to push. Thank you. Oh.
World News Tonight with Peter Jennings continues. Now, solutions.
There are several ways to dramatize tonight's solution. We could tell you that a horizontal asphalt infrastructure anomaly is a curse for millions of American drivers at this time of year. That would be potholes to most of us. We could tell you that $52.5 billion a year goes to highway construction and maintenance, not to mention all the other money to repair the bridges and the other pieces of the nation's infrastructure. It is safe to say, we think, that if the ancient Romans were watching tonight, they would be asking, what took you so long? Here's ABC's Jack Smith.
Roads and pavements. Bridges and support columns. All of what's called America's infrastructure is slowly crumbling because what it's made of does not last.
This is ordinary concrete, and this is what happens to it after years of punishment. It falls apart. Most of the concrete in the nation's highways and bridges has a life of just 30 years.
What's the solution? I'm standing on it. Brand new stuff called high-performance concrete. This is a sample. Engineers say this will last not 20 or 30 years, but 100 years, maybe longer. This is what America's roads and bridges could be made of in the future.
Engineers at the New York State Department of Transportation discovered how to make it 2.5 years ago.
We were surprised when we actually did all the calculations and got the test results back and said, my goodness, this really is going to work.
Researchers stumbled on the formula after the Clean Air Act forced power plants to reduce pollution. Huge quantities of industrial waste called fly ash began piling up, collected from smokestacks. At first used as a filler in cement, it turned out to be a key ingredient in strengthening it.
So this is 1/4 industrial waste. But it makes the cement many times tougher.
That's right.
High-performance concrete is 74% cement, 20% fly ash, and 6% microsilica, another type of ash, all mixed with water. When it dries, ordinary cement is actually porous, not solid. That's how salt and water get in. But the fly ash and microsilica are 10 to 100 times finer than talcum powder. And Professor Ken Hover of Cornell has found they literally fill in the microscopic holes in the cement and demonstrates it with colored tennis balls.
So the next thing I would want to do if I want to densify this box is get some mid-sized particles and take those mid-sized ones and try and get them into the box.
They fill in all the smaller voids in between the cement particles, and we just have a very, very dense material.
More waterproof?
Correct.
Stronger?
Yep.
Lasts longer?
Yes.
The new concrete is 3 times more water resistant, 20 times less likely to form cracks, and in pressure tests
9,060 psi.
has proven almost 20% stronger than regular concrete. However, modern scientists were not the first to make high-performance concrete. The ancient Romans were, mixing volcanic ash with their cement to make it far tougher. It's one of the reasons the Colosseum and other Roman buildings have lasted so long.
We really literally reinvented what our ancestors 2,300 years ago had already done.
At least 11 states are following New York's lead. High-performance concrete is more expensive than ordinary concrete, but because it's easier to lay down, costs about the same to use. Engineers say not only could it be an answer to much of America's infrastructure problems, but it could revolutionize all construction. Jack Smith, ABC News, Albany, New York.
They use the term microsilica in that video, and that's just another term for silica fume, which is the group that we're here talking about. As you know from newscasts, most newscasts are written to an 11th grade level. So that was the introduction to high-performance concrete as ABC News conveyed it back in February 11th, 1997, 9 years ago. So that map they showed of the 9 states or 8 states that have used high-performance concrete, right now that map is complete. Every state has used high-performance concrete on their bridges. We'll talk a lot about what Illinois does on their bridges here and what they've done down here on Interstate 70 and up along 294 in Chicago as part of the presentation. But that's kind of the background. The idea is that even though this is, that they said it was invented 2.5 years before they shot this video, so that would have been 95. Reality is Ohio put down the first bridge in '84 with silica fume concrete, and New York did their first bridge in 1986. The state DOTs have a way of studying things for a long time before they flip a switch and go with it for full specifications. So they looked at this material in place for a number of years before they went ahead and switched over and started doing all their bridges with high-performance concrete. New York and Ohio are 2 examples that since 1997, every one of their structures having to do with a bridge has been built with high-performance concrete, the mixed design that they showed you there, those compositions. Illinois, every state is a little bit different in their learning curve. Some states, to give you an example, I'm from Pennsylvania, and sorry to say, I think we only have 4 bridges that I would consider high-performance concrete by design, where you go to Ohio and New York and they probably have thousands already in place. And that's what this whole idea of technology transfer is we don't want people to have to reinvent the wheel. We already know how to do this. The technology's already in place. We need to get it out there and in our industry, in the construction industry, and begin using it. The problem is that most of the technology that we use in the construction industry, help yourself, that we use in the construction industry is 30, 50 years old. We still place concrete the way they did, our fathers and forefathers before us still place concrete. But as you saw in that one video there, the one fellow mentioned about the Romans and the idea that we're going back to that technology, and that's, you can pop that off. That's where we'll try and start. When people think of high-performance concrete, a lot of times they think of strength. If a little bit is good, a lot must be better. And in a lot of cases, that's good. If you're doing a high-rise building, this is 311. This building next to next to the Sears Tower in Chicago is 311 South Wacker. Which light? They used high-strength concrete as the columns in this building. This is some 14,000 psi concrete, 6 million modulus of elasticity. Runs from the foundation all the way to the top of the building here. The idea of using a high-strength concrete, if you were to design the building with 4,000 psi columns, the columns would be very, very large to support all that weight. If you can make the concrete stronger and stiffer, then you can use a lot less columns to support that same dead load. Well, if you're Trump and you're leasing it at what, a couple thousand a square foot, that extra square foot that you save by reducing that column size on every floor more than pays for any cost differential for high performance concrete, or in this case high strength concrete.